Okay, so now that we've talked about powers and stuff like that, we're actually going to simplify things just a little bit. Because with powers, we can really identify that as an exponential model. So we can kind of write that as an exponential model, or we can write as a logarithmic model. And so what we're going to do, not all curved relationships are described by power models, but we can modify with logarithms and exponentials. And we can also go back to the power models. And so we're going to learn a little shortcut today about how do you know if we should use logarithms and exponential functions, which are related to each other, or do we use our power models, which would be like squared, square roots, or even reciprocals, because reciprocals are a -1 power. And so what do? So we can use logarithms to transform an exponential model by logging our explanatory variable values or logging our response variables. So typically we use a logarithm to go ahead and try out either one to figure out which one gives us the most linear pattern. And if you're not sure, we can go to our residual plot to see which one gives us the best residual plot. So we have a sample problem. A student opened a bag of M&Ms, dumped them out, ate all the ones with an M on top. When he finished, he put the remaining 30 M&Ms back in the bag and repeated the same process over and over till the M&Ms were gone. So here's a table and scatter plot. Okay, so the first time he flipped it out, he had 30 M&Ms after he ate all the ones with M's on it. The second time, he flipped them out, ate all, and there were 13 left. And after 3, there were only 10 left. After 4, there were 3 left, so on and so forth. So here's our data. This is our L1 and our L2, or our X and our Y. And so when we graph that, we can see the information. So 1 and 30, 2 and 13, 3 and 10. And so obviously, it is curved data. And now what we have over here, graph number 2, is a scatter plot showing the natural log of the number of M&Ms. So we logged our Y value, and we used a natural log, LNY. And the last observation of the table is not included because I can't ln 0. That is an undefined value. So we had to just kind of cut that out. Why would it be reasonable to use an exponential model to describe the relationship between the number of M&Ms remaining and the course number? And the real main idea that we have here is that when we transformed this Y value, we end up with a really strong, I mean, look how close that is to a straight line. A super strong negative linear association when we transformed the Y value. Okay, so now we actually have a computer output that gives us the information. What would the equation of the least squares regression line be? So here is our y-intercept. Here is our slope. And remember, we transformed our y value. So this is really going to be the natural log of y hat, because that's what we transformed was the y value, equals 4.0593 plus negative 0.68 x. And then if we're dividing our variables, this is going to be the natural log of M&M's remaining equals 4.0593 minus 0.68 course. They said course. I think turns is probably a better word. So the number of times you turn out those M&Ms, whatever. Use your model from Part B to predict the original number of M&Ms. So the original number of M&Ms means that I have 0 turns. So the natural log of M&Ms equals 4.0593 minus 0.68 times 0. So this just kind of goes away because it's times by 0. And so now I have the natural log of M&Ms equals 4.0593. And then the next thing is, well, how do I get rid of that natural log so I can figure out how many M&Ms I have? So to get rid of a natural log, what we do is we do the inverse of the natural log. So natural log is a log base e. So I'm going to base e both sides. So this is really now e to the natural log M&M's power, and this is now e to the 4.05 power. And so this will cancel this out, giving me predicted M&Ms left equals whatever e to the 4.0593 power is. And when we calculate that, we get 57.9337. So there was approximately 58 M&Ms to begin with. So Part D now is saying, hey, now here's my residual plot. Does this really tell me that the model works or not? Since there is no curve, no distinct pattern, our scatter is good, so yes, it is an appropriate model. Okay. So, which transformation do we choose? Here's your shortcut. So, it's going to be a power model if you can log both the variables and get a linear equation. So now we don't have to sit there and mess around with the squareds, the square roots, and all of that. We'll know it's a power model if I can log both sides, both the x and y, and we get a linear pattern. It's going to be exponential if I log one variable and it's relatively linear. So that allows us to not mess around with the powers anymore, and we can just use our logarithms now to help us figure that out. So what we have is we have data looking at distance and period for just a certain random thing. I just kind of found these somewhere. And what we did here is we have the distance and the natural log of period. Because there is one variable being logged, this is an exponential model. And then on our next one, we have the natural log and natural log. Since both of them are being logged, this is a power model. So looking at the graph, which one's most appropriate? And definitely the power model. It is way more linear. Okay, so rheumatoid arthritis patients are often treated with large quantities of aspirin. The concentration of aspirin in the bloodstream increases for a period of time after the drug is administered and then decreases in such a way that the amount of aspirin remaining is a function of the amount of time that has elapsed since the peak concentration. The table shows the data for a particular arthritis patient who has taken a large dose of aspirin. Use the data to predict how much aspirin remains in the patient's bloodstream 12 hours after the 15 milligram rating. So here is our data. And what we have here is we have the original scatter plot. We have hours and the blood, the amount of aspirin left in the blood. And it looks pretty straight, but if you look really carefully, it's kind of curving a little bit. And how can we tell, really, is that curving or not? Is it just a figment of our imagination? Well, we look at our residual plot. And we can definitely tell that it's curved because it's curved here, which means that it's curved in the original. So the scatter plot tells us there is a strong, because is strong, negative association but it is curved. So a linear model is not appropriate. So now what we did is we transformed it 3 different ways. Here we have the natural log of hours, and here we have the natural log of concentration, and here we have the natural log of both. And so what type of model is each? So this one has a natural log of 1, so this is an exponential. This has a natural log of 1, so this is also an exponential model. But this has a natural log of both, so this is a power model. So now what we have is the computer regression for each one. So now we have to write our equation for each one. So let's go ahead and start with the first one, which had the natural log of our, the natural log of our x. So when we come back, we're going to have y hat equals 13.1048 minus 4.4027 natural log of x. Now for our next one, we natural logged our y's. So now this would look like natural log of y equals 2.7051 minus 0.1785 times x. And then our last one, we natural logged both. So natural log of y hat equals 2.6906 minus 0.5953 natural log of x. And now that we have our equations, we're going to go ahead and we're going to predict each one. So we're going to predict what happens if we have 15 hours after peak concentration. So hours is our, we need to double check. We can go back. Hours is our x value. So we're going to go ahead and plug in 15 hours. So this one's going to be y hat equals 13.1048 minus 4.4027 times the natural log of 15. And so now this is simple calculation, natural log of 15 times this, and then add that to it, and we get 1.18206. Now we're going to go ahead and go to the next one. So natural log of y hat is going to be 2.7051 minus 0.1785 times 15. So we go ahead and calculate everything, and we get to natural log of y hat equals 0.0276. And then we've got to get rid of the natural log, so we base e both sides, so that cancels out to get y hat, and now we have to e to the power of 0.0276. And I get 1.2028. So now we're going to move on to the last one. So natural log y hat equals 2.6906 minus 0.5953 times by 15. Oops, natural log of 15 ln 15. So we now natural log 15 at times by that. We get now natural log of y hat equals 1.0785. We base e both sides, so that cancels that out, and we get y hat equals 2.94023, or 03. Didn't 403. There we go. Didn't round correctly. So now we get different values, and so the main idea, which one is really the most appropriate? And so we do several things to see which ones are most appropriate. We look at the residual plots, and the residual plots really can make a big difference. So we can definitely see, hey, I've got this here, and I have kind of a curve, so this one's no good. This one has some good scatter, and this one, hey, look at that. That looks very similar to the first one. So really, the most appropriate one is the second one. And we can also double check that by looking at this. Do not do this alone, because this alone may be a little misleading. Look at the residual plot and then go back and double check those values. And we can see that is a really good R squared. And so our second equation is really the best one for our data.